There we go. Today's lesson is on projectile motion. Now, projectile motion, or a projectile, has gravity. I should make this look better. As the only force on it. So a projectile is something after you've thrown it or after it's come out of the barrel of a cannon or gun or slingshot or whatever other thing is hurling it, okay? So while you're throwing a baseball, you are exerting a force on it with your hand, but when you let go, the baseball flies through the air, and if we ignore air resistance, the only thing happening to that baseball is that gravity is pulling on it, and that's going to shape its trajectory. That's another word we need to kind of throw out there. Trajectory is the path of a projectile. So this Latin word root ject, what the hell is my camera doing now? There we go. This Latin word root ject must mean somehow to throw or hurl or something like that. I guess that makes sense. When you're ejected, you get thrown out. So there you go. I like to introduce this concept. In fact, I'm going to take the caps off of all my pens because I don't need them today. I like to introduce this concept by talking about a football kickoff. And this is a football kickoff as seen from some weird places. In one case, it's the end zone. Now imagine you've got seats in the end zone, and especially if you're at, say, the Rose Bowl, the end zone is very far away from the center of the field. There's, all kinds of extra space and track and field stuff and all. Or maybe that's the Coliseum. Yeah, I think I got those two confused. Anyhow, so what happens is when they kick off the football, you see the football rise a great deal into the air, and then rise a little lesser amount, then rise a little lesser amount, then rise almost not at all, and then don't rise at all, and then fall more, and then fall more, and then fall more. This is accelerated motion. And because we're in the end zone, we don't see the football coming towards us or getting further. We just see one dimension of its motion. We just see its up and down motion, and it's accelerated because it is fast, slower, 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 stop, then faster, faster, faster on the way down. If you were to watch that very same kickoff from a different perspective, let's just say you were in a drone or a blimp far above the stadium, you would see that the football would move the same distance in equal intervals of time because this is constant velocity motion. So when you have accelerated motion in the vertical direction and constant velocity motion in the horizontal direction, and this is as seen from the blimp, the real motion is both of those put together, and that's what somebody would see if they were on the 50-yard line. Now, this is the fun part for me. Here we go. The football starts on the ground. In the first instant of time, the football rises a great distance into the air, travels horizontally a constant distance, and winds up right there. In the next instant of time, it rises not quite as much, travels horizontally the same distance, and winds up right there. In the next instant of time, it rises very little, travels horizontally the same amount, and winds up over here. In the next instant of time, it doesn't rise or fall, but it still travels horizontally the same amount and winds up over there. And then, of course, it begins to fall. First, a small amount, but travels horizontally the same amount and winds up right here. And then falls a greater distance, travels horizontally the same amount, and it's over, and then it falls a tremendous distance, travels horizontally the same amount, and hits the ground right here. So this is the accelerated motion in the green arrows and the constant velocity motion in the blue arrows, and you'll see that what this does is it creates a path for the football which has a shape that you might recognize as a parabola. The trajectory of a projectile is a parabola, and that's all because the x and y directions are independent. The most important thing you can say is that the y motion is independent of the x motion. The y motion is doing this accelerated thing. The x motion is doing this constant velocity thing, and you wind up with this beautiful parabola. Okay, this is ignoring air resistance. In real life, these blue arrows would slowly be shrinking, and you'd wind up with a truncated kind of parabola. So if you're really playing sports, you have to take that into consideration. But if we ignore air resistance, we get most of the answer right away. This works not only for something that's being launched off the ground, but it also works for something that's being launched horizontally. For example, if we go to the top of a cliff over the ocean and we set up a cannon and we fire a cannonball, why then the cannonball is going to go horizontally and wind up over here and, well, hold on a second, I forgot to include the vertical motion, and drop just a little bit and wind up here. Then it's going to go horizontally the same distance and drop a little further and wind up down here. Then it's going to go horizontally the same distance. Oh, I got a little carried away there. And drop even more and wind up down here, and I think that's just about it. That's where the ocean is. And you'll see that this is also a parabola, but it's a parabola that's half a parabola downward. That's the shape of that trajectory. So there's this famous problem in physics, and it's called the monkey hunter problem. And it goes something like this. There's a hunter standing over here, and there's a monkey. I don't know how to draw a monkey. Maybe we'll just put some ears on a stick figure. And the monkey is in the tree, and the hunter points his rifle directly at the monkey and fires the gun. But the monkey is startled by the flash made at the firing of the gun, and so the monkey drops out of the tree and falls. And the question is, does the bullet hit the monkey or not? And most people would be inclined to say, no way. That bullet is going to go along this straight line where it was aimed directly at the monkey, but the monkey will be well below that. And the answer is no, because the bullet is not going to travel along this straight line. The bullet is going to be pulled below that straight line along a parabola, and it will fall the exact same distance as the monkey falls in the exact same time, because the acceleration of all bodies acted on by gravity is the same. So the bullet will actually, if aimed directly at the monkey and the monkey drops out of the tree, the bullet will hit the monkey. The very surprising fact is that bullets don't go the direction they're aimed. They always fall below that line. This is, like I said, called the monkey hunter problem, and because it offends people nowadays, they've changed the phraseology. Now it's a banana cannon that shoots a banana to the monkey, and you're feeding the monkey, and the monkey drops out of the tree, but the monkey still gets the banana. I think we all need to just take a breath. This idea that the projectile drops below its intended line of flight is really important for you to get into your mind. And actually, it had ramifications in the U.S. Army. Between the Korean War and the Vietnam War, the U.S. Army had changed the main battle rifle for its troops and had changed over to the M16, which is the military designation of the AR-15 platform of rifles. But the most spectacular thing about the AR-15 platform of rifles is the cartridge that they use. It's a very fast, very lightweight bullet. So it comes out of the barrel very quickly, and so it goes along this path and drops a lot less away from the intended path than a heavier bullet from an old-fashioned like World War II style rifle would drop. And the idea was that that soldiers that were scared and would have a tendency to just point their rifle at the enemy and pull the trigger, not to use the sights or do any kind of fancy aiming slightly above kind of thing. And that with the faster projectile, they would be more likely to hit their target because it would drop less than a slower moving projectile would. Also, the smaller bullets meant you could carry more ammunition, and since the average infantryman was now going to be given a rifle that was capable of automatic fire, carrying around some ammo would be kind of a cool deal. The downside, as reported by the troops in the Vietnam War, was that the projectile was a little less lethal. They had to shoot people more than once to get them to stop doing what they were doing, and so that was the trade-off. Nowadays, the Army is very close to adopting a brand new rifle for everybody, and you'll notice that the caliber of the rifle is going to be larger than the one that's used by the M16, and that's because they realize that even though they are going to have a drop-off problem, they really do need the projectile to be a little more lethal. Okay, so where was I going? Monkey hunter problem, blah, 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 blah. So let's talk about practically how we're going to solve these things. Okay, so in the past, when we were doing one-dimensional motion, let's go ahead and use the blue one here. When we were doing one-dimensional motion, we had, oh gosh, I love this, the way this thing focuses. We had some variables. We had a starting position, we had a final position, we had a starting velocity, we had a final velocity, we had an acceleration, and we had a time. We also had 4 equations of motion. The Swiss Army equation, my fave. The definition of acceleration, my second fave. We had the no-t equation. My third fave. And the one I use the least for some reason is the no-a equation. I keep forgetting it exists. Kind of like if you have kids, you forget the youngest one even exists sometimes. Oh, I know. Sorry. Talk to my sister about that. All right. So what are we going to do when we move into two-dimensional motion? Well, we're definitely going to have twice as many variables. We're going to have a starting position in x and y, a final position in the x coordinate and the y coordinate, a starting velocity in the x direction and a starting velocity in the y direction. We're going to have a finishing velocity in the x direction and a finishing velocity in the y direction. We're going to have an acceleration in the x direction and an acceleration in the y direction, but we're only going to have one time. So it's not 12 variables, which would be double 6. It's 11 because time does not belong to x or y. Time is a separate dimension. Although we're going to treat x horizontal and y vertical motion separately, time is shared by both of them. Also, it's not 11 variables because this one's typically 0. And it's not 11 variables because this one's typically positive or negative 9.8 meters per second squared. And it's not 11 variables because if you choose your coordinate system correctly, you can always make those two 0 by putting the origin of your coordinate system wherever the object starts. So really, it's not twice as many variables. It's 11, 10, 9, 8, 7. 7 variables. So it's only slightly harder, although there will be multiple equations, but they are kind of easy to figure out. For example, the x version of the definition of acceleration. Okay, Harmon, that's really not what I wanted to write. The x version of the definition of acceleration has a mirror image that's useful for y. And all you have to do is change the y subscripts, the x subscripts into y subscripts. So there are twice as many equations, but they're the same 4, just recast and used for y and x directions. So that's how we're going to solve these problems. Shall we do one? I think we have just enough time to do one. Let's go back to that cannon problem. Let's set it up so that we have a cliff overlooking the ocean. Let's make the cliff 20 meters high. That's about 60 some feet high. And we're going to put a cannon on top of the cliff, and we're going to fire a projectile at 30 meters per second. That's about 65 miles an hour. I really don't know what speed cannons fire at. I don't know. They use gunpowder. They're probably a lot faster than this, but what the heck. And what I want to know is this cannonball is going to go on a half a parabola, and it's going to land in the water over here. I'd like to know, where is it going to land? Now, in order to figure that out, I first need to choose a coordinate system. And I'm going to choose the origin to be where the cannonball is launched from. And I'm going to choose the positive directions to be down and to the right. I'm allowed to choose any coordinate system I want. That's my choice. And now we need to fill out the list of knowns and unknowns. So let's do it. Xi is 0. Yi is 0, because I chose that. Xf is where it lands in the water horizontally, and I don't know what that is. Yf is where it lands in the water vertically, and that's 20 meters below the launching point. I do know that one. Vix is 30 meters per second, and Viy is 0 meters per second. Now this one's going to surprise you. Vfx is also 30 meters per second. How do I know? Well, that's because the acceleration in the x direction is 0. Vfy, however, I don't know. Acceleration in the y direction is going to be 9.8 meters per second squared. And now we've got the list of knowns and unknowns in 2 dimensions. We're ready to rock and roll. Now we're being asked for xf, and it makes sense. Oh, and time. Time is shared for both of them. We don't know what it is. It makes sense to try to get xf from this information right here, but you're going to find out that we can't. First of all, we don't know time, so we have to use the no time equation. And if you put the no time equation in x, if you write it down, you're going to discover that this term right here turns into 0. And it gives you back that your final and initial velocities are equal. But because the acceleration is 0, it just canceled out your xf. You can't find xf this way. So this is a dead end. So what we wind up doing is we wind up realizing that we need the time. And the time is actually best to get from the y side of things. So let's write down the y Swiss Army equation, which is my favorite. And let's put in this information. 20 equals 0 plus 0 times t plus 1/2 of 9.8 times t squared. Oh, that's cool because 0 is 0, and 0 times t is 0, and half of 9.8 is 4.9. So 20 equals 4.9 t squared. And when you do the math, you find out that t is 2.02 seconds. So I wasn't asked for the time, but I found the time because I need the time in order to figure out how far this thing goes. And now we can use the Swiss Army equation in the x direction to figure out how far this projectile goes. Xf is going to be 0 plus 30 times 2.02 plus 0, or Xf is going to be 60.6 meters. That's how to solve a 2-dimensional motion problem. Same 5-step problem solving method, more variables, and 2 kinds of things. You have to work in the y direction and the x direction. Okay, that's a lot to throw at you in one day, so I'm going to stop there.